Welcome. I'm studying for the breadth exam at UNCC, and two questions that will come up on the wireless communication part are regarding shortest path, and then determining the shortest path based off of two methods. So the two methods that I have looked at are the Dijkstra method and the Bellman-Ford method. Now, the Bellman-Ford allows you to do shortest path calculations using negative weights, whereas the Dijkstra may make a mistake with that. Now, the Bellman-Ford method allows you to look at the diagram as shown here, and we will determine the shortest path from 1 to node 2, and then we would look for, we're looking to determine the shortest path to 2, to node 3, to node 4, to node 5, or to node 6. And the way we go about that is we start with one node. And we always try to start with the node closest to the first node. So when we're at node 1, we can either go to node 3 or node 2. So let's start with node 2, and we look at what are all the paths that are possible to node 2. So we see there's only one path, which is node 1. So we write 1 with a cost of 2. Then we go to a node that 2 can hop to, which is 3. And we say, well, what are the costs to get to node 3 given we know node 1 and node 2? So node 1, the cost will be 4. So we write 1 and 4. To go from node 2 to node 3, we know that it is a cost of 2 plus 1, which is 3. And we say, since the cost to go from 2 to 3 is lower than the cost to go from 1 to 3, we say the shortest path to 3 is from node 2, given we have the ability to go from 1 to 2 to 3. Then we look at node 5, and we say, well, what are all the paths that can go to node 5? We see only one path from node 3 to 5, so we write 3 with a cost of 3 plus 3, which is 6. For node 4, we see that there's two ways to get to node 4, and we have the shortest path for node 2, and we have the shortest path for node 5, so we say that the cost to go to node 4 from 5 is 6 plus 2, which is 8. And the cost to go to node 4 from node 2 is 2 plus 7, which is 9. Now we see that the cost to go from 5 to 4 is lower, so we use that as the shortest path to go to number 4. Now we look at the shortest path for node 6, and we say, what is the shortest path? We would indicate that from 4 to 6, the cost is 8 plus 1, which is 9. To go from node 5 to 6, the cost is 6 plus 5, which is 11. So the shortest path to get to node 6 is 9. So we can look at this to verify, and we would be able to draw this path that shows the shortest path to node 6 from node 1. Similarly, we have another problem here that is a little bit more dynamic, or a little bit, not dynamic, but a little bit more complex. And we see that applying the same method we did using Bellman-Ford's methodology, we were able to determine the shortest path to node 7 from node 1. Now, if you go with me, we go from, we know that node 5 to node 7 is the shortest path, and we know that from 5, node 2 is the shortest path, and we know to get to node 2, node 3 is the shortest path, and we know to get to node 3, node 4 is the shortest path, and we know to get node 4, node 1 is the shortest path. So we have illustrated this drawing right here to indicate the shortest path to get to node 7 from node 1. Now, looking at the Dijkstra method, what we need to look at is our iterations. So we have, for the number of nodes we have the same number of iterations. So we have here 2, 3, 4, 5, 6, 7 nodes. So for Dijkstra's method, in order to find the shortest path, we would need to have 7 iterations. Above here, we see 1, 2, 3, 4, 5, 6 nodes. Using Dijkstra's method, we would need to do 6 iterations. Now, an example of 6 iterations can be shown here, and we would indicate how many nodes we are able to access based on each iteration. So once we reach the 6th iteration, we should be able to access all of the nodes in the diagram. So we pick at random. It doesn't have to be random. It can be whatever order you want, as long as the nodes are able to be in contact with one another. So you can't pick 1 and then pick 6. You have to pick 1, then 1, and then a node that it's connected to, and vice versa, until you reach the 6th node. So normally how they have done this in the past is 1, 2, 3, 4, 5, 6. So we start off with 1 we would have connected to, but I chose to do 4 because 4 is in contact as well. 1, 4, 2, then 1, 4, 2, 3, 1, 4, 2, 3, 5, 1, 4, 2, 3, 5, 6. From there, we look at the lowest cost to reach node 2 from the selection of nodes that we can use. So I looked at using node 1 to get to node 2, and I realized there was a cost of 2, and the path was 1 to 2. Always on the right hand side here, you will be using the node that you're trying to reach, which is node 2. So for here, we're trying to reach node 3, so we always have 3. For here, we're trying to reach node 5, so we always have 5 at the end of the path. And in the beginning of the path, we can pick any of the nodes here, and anything in the middle of the path as well, we can pick any of the nodes that are available to us here. It limits our path, and it also adds computation. At the end of it, though, in order to reach our destination L6, you can see that for a complicated circuit like this, where there's several paths that can be taken to one destination, rather than manually having to go through each one, we can just use a table as this to compute the shortest path from node 1 to the farthest node to the right, which would be node 6 in this case. And we can see that 1, 4, 5, 6 has a weight of 4, which is the shortest path to get to 6. Thank you for listening, and stay tuned for future videos on how to understand networking and data structures and data communication.